Hello and welcome to my video lecture, A Gentle Introduction to the Calculus of Variations. My name is Spencer Bagley. I'm at Westminster College in Salt Lake City, Utah. You can find me on Twitter or on WordPress. And you can find these slides at the link there. That's a handout version of this Beamer presentation, so it doesn't have the animation, but it does have, all the information about what we're doing so that you can look at it more at your leisure later. Here is a vague outline of the talk. We're going to start by looking at a motivating problem, one that's interesting, but it's also going to be too hard for us immediately. So we're going to think about an easier problem instead. That will help us decide what the general approach is, and then we'll go back and apply that to the motivating problem. A bunch of fun math stuff is going to happen here. We're going to talk about functionals. We're going to talk about differentiation under the integral sign. We're going to do integration by parts a couple of times. A very small amount of differential equations, and then Lagrange multipliers make a surprising appearance at the end of the talk. Okay, so here is the motivating problem, and it's called the catenary problem. So catena is Latin for chain, and so the question here is what is the shape that a hanging chain takes? Specifically, can you write it down as a mathematical function? If you look at this, you could sort of say, maybe it's an arc of a circle, maybe it is an arc of a parabola, maybe it's something else, I don't know. And so that's sort of the interesting problem that we're going to try to answer at the end of this talk. But that's clearly way too hard for now. So let's back up and we'll think about an easier problem, and we're going to think about it in terms of functionals. Now, what is a functional? It's a kind of function. Okay, what is a function? A function is some kind of rule that associates inputs with outputs. Most of the time with the functions that we're used to dealing with, we think of functions as maps from the real numbers to the real numbers. So we have one real number input and we're associating with one real number output. Okay, well, a functional is just a function who eats functions and tells you numbers. So the inputs are functions and the outputs are numbers. So you might write it like this. The letter J, capital J, is traditional for some reason. Don't ask me why. We're probably going to think about functionals on C2, which is the space of twice continuously differentiable functions. That's smooth enough for our purposes. There are, of course, other function spaces that we could play with, but that's as spicy as we need to get. By the way, if I were naming this subject, I would call this subject the calculus of functionals rather than the calculus of variations. Nobody asked me though, unfortunately. Okay, what are we going to do? Here is an example of a functional, arc length. If you click on this link, it will take you to the Wolfram Alpha page for arc length. Or if you just go to Wolfram Alpha and type in arc length, you will get a cool little calculator. Let me show you what that looks like. Okay, here's the Wolfram Alpha page for arc length, and you can see what's going on is we tell it a particular curve, a particular function, and we tell it the x value that we want to start at and the x value that we want to end at, and it calculates the arc length of that function between those 2 points. All right, so the sort of default settings on Wolfram Alpha are sine of x from 1 to 2, and it does whatever it does, and it tells us that the answer is 1.04, and it draws us a nice little picture. Okay, we could throw in some other function here, like, I don't know, x squared. That's a fine one. And it, again, does whatever it does, and it tells us some number, 3.16, and you can see this picture, the arc length between x equals 1 and x equals 2. It's the length of this piece of line. Okay, cool. So my point with this is, legitimately, this is a function whose inputs are functions, right? If I put in a function, I get out its length between two x values. Let's see if we can write down what Wolfram Alpha is actually doing in the background here. And to do that, we're going to do a little calculus. We're going to slice, approximate, integrate, which I like to think of as the fundamental paradigm of integral calculus. So here's some arc, and I'm going to look at a little piece of it, and I'm going to approximate the length on this purple curve by a straight line, which I'm going to call ds. I don't know why we always call lengths s, probably German or something, whatever. This is not the right answer, clearly. The purple line is a little bit longer because it bends away from ds. But it's a pretty good approximate, right? And what's more, it's easy to calculate. Specifically, it's the hypotenuse of a right triangle with sides that I can think of as dx and dy. And so that means that ds squared ought to be dx squared plus dy squared. I'm going to play a fun trick and factor out a dx squared like this, because then I can recognize this as, oh, look, that's dy dx all squared, which is the derivative. I can take the square root to get ds by itself. I'm not going to worry about plus or minus because it is a length and I want to think of it as positive. And so I end up with the following. We're going to see this a lot, that ds is the square root of 1 plus the derivative squared dx. So hold that thought. We'll see that multiple times. All right, now that we have figured out the length of a little chunk, we can add up a bunch of those and take the limit, and then we get an integral. And here then is the formula for this functional. Now you'll see I'm writing it with brackets. That's also traditional, rather than parentheses, to indicate that it's a functional rather than just a function. Nice little thing. Okay. Notice here that this integrand is some function that involves, it for sure involves y prime. Maybe I could think of it as involving also x and y in later instances. Some notes here, most functionals that we care about end up being definite integrals because this slice integrate approximate paradigm is so useful. And many of the functionals that we care about, like the one that we have here, don't end up having x explicitly in them. Because things are autonomous, I can shift them from side to side and nothing sort of bad happens. Okay, so then here is our easier problem that we're going to solve. What function connecting two given points has the minimal arc length? Of course the answer should be the straight line. I'm asking a question that I know the answer to so that I can figure out the right way to figure out the right process to get the answer. Okay. We're going to need a little more technical tools here, and the tools that we're going to need, I like to call them wiggles and then variations. This is where the calculus of variations comes from. Okay, what is a variation? Variation is a function that I'm going to denote as eta of x, and it has a couple of interesting properties. First of all, it's not too wild. Maybe I want it to be piecewise C2. And then I also want it to be 0 at the endpoints, and I'll tell you why in a second. Those are the endpoints of the definite integral, the region of integration that we're interested in. And then a wiggle is what I call, and this is not a standard term, this is what I call what you get when you add some amount of variation to a base function. So I'm going to write it like this. A wiggle is our original y of x plus a times eta of x. What is that a doing? It is giving us a one parameter family of curves that includes the original y of x, specifically when a equals 0. And so you can think of a as the amount of the variation that we are going to add to our original curve. Okay, what is really, why are we doing this? It's because we want to take some kind of derivative, because the right answer to our question is the one that minimizes or maximizes a functional, and derivatives are a good technical handle on extrema. And so what a derivative asks is what's the effect on the output of small changes in the input? And so since our inputs here are now functions, I think that wiggles are a good technical handle for us to deal with small changes to functions, small changes to our input. Okay, let's take a look at what this looks like. And I've got a Desmos pulled up here on one of my various pages. So here I have the straight line that connects the points 0, 0 and 2, 4. And I've asked Desmos to calculate the arc length. It's this, which is indeed the square root of 20, as we would expect. I also have here a variation. So you can see that this satisfies the criteria that we have. It's 0 at the endpoints, and it isn't too wild. And then here is a wiggle. So what I'm doing is I'm taking this red thing and I'm wiggling it by a certain amount of the black thing. And I can change the amount, and you can see that, right, sort of perturbs the red function in just a little bit. What's neat about this setup is that I could use different functions for h of x, here's a wigglier one. How about the sine of 2 pi x? All right, well, so now you can really see that's really a wiggle. And I again have control over the amount of the wiggle. And I could get wigglier, right? I could put any function in there that I want and still end up with some purple curve that connects the 2 points that it's supposed to connect. What's more, I have asked for the arc length of the wiggle, and you can see it's in general going to be a little bit larger than the arc length of my minimal thing, unless of course a happens to be 0 and then they coincide. Okay, cool. So that's what's going on here. And here's my point. If I throw the wiggle into the functional, here's what I get. And truly, this is a function, a regular, plain old R to R function of A, of the amount of wiggle, of variation, that is. And so if that's true, right, so I can write it literally as J as a function of A. And here is what it would be. And if that's true, then I can take a derivative with respect to A. And what's more, if my original function is a minimizer, right, that's the one that corresponds to A equals 0, which means that J prime at 0 ought to be 0. And so I feel like that's a technical handle that I can use to calculate anything in this weird situation. Okay, well that's going to involve differentiating an integral, for which we're going to need to use a fun trick called differentiating under the integral sign, or the Leibniz integral rule. Sometimes it's called the Feynman integral trick, but honestly he's kind of a jerk, and so I don't want to stick his name on it. As long as the integrand is continuous in the region that we care about, which I promise it is, you can interchange the order of the integral sign and the derivative sign, but then we need to think of the derivative sign as a partial derivative because now there's one more variable going on. If this reminds you of Fubini's theorem, that's because it is basically Fubini's theorem. If this reminds you of Clairault's theorem, it's basically Clairault's theorem. I'm not going to prove it. You can think about what a proof would look like. It's not too bad. All right, so let's do this calculation, and I'm calculating toward the idea that J prime of 0 ought to be 0. All right, so I've got the derivative of my function of A. I've done my differentiation under the integral sign trick. Let's do the calculation here. Works out to be this, and if I simplify a little, here's what I get. And now I want to think of this when A equals 0, right? And so I'm thinking of evaluating the derivative at the point A equals 0, and I'm told that I'm supposed to get 0, right, by my hypotheses. And here's what I really get when I substitute 0 in. All these A's die, and they take those eta primes with them that are inside, and the only eta prime that's left is this one that lives out here. Okay, cool. Boy, this is still just a mess, though. I don't really know what to do with this. What we're going to do with this is we're going to need a lemma, and it's called the fundamental lemma of the calculus of variations. And I love whenever something that's called fundamental comes up. Here's what it says. If you integrate a continuous function against a variation and you get 0, no matter which variation you choose, well then the function has to be identically 0, right? The constant function 0. Okay, let's see how the proof is going to go. The proof is fun. It relies on a little bit of analysis, but nothing too scary. We're going to do it by contradiction. We're going to suppose not. We're going to suppose that m is not the constant function 0, which means that somewhere it's got to either be above 0 or below 0. Without loss of generality, we'll say above. There has to be some special x star where it's above 0. Okay, and then our hypothesis was that the function was continuous, which means that I can take that point where we're above 0 and I can fatten it up into a whole little interval where m is greater than 0. I think maybe a picture would be helpful here. Here's my x-axis, right? Zoom. Beautiful, that was nice and straight. Here's my function m. If it's non-zero somewhere at this x star, well then it has, since it's continuous, it has to be non-zero on a little interval around. All right, cool. So we're gonna say we're gonna make up a function eta, which is 0 outside of that interval, and then it does this little parabola thing on the interval. So I'll sketch that function. Looks like this. Here is c. Here is d. We're going to go 0, parabola, 0. So this is clearly a variation, right? It satisfies our definition. It's piecewise C2. It's 0 at the endpoints because it's 0 off of this small interval. All right. So by our hypothesis, we were integrating m against this this variation, and we were getting 0. Okay, I'm going to split up this integral into 3 pieces, and I bet you can guess what those pieces are. You're right. They're precisely the piece between where we start in C, the piece between C and D, and then the piece between D and where we end. All right, and the reason that I'm doing that is because eta of x is in fact 0 on this interval and on this interval. And so these two integrals will die. And then what's more, this one, right, eta of x is positive because it's the upward parabola by our choice. And m of x is also positive on that interval. So I got a positive thing times a positive thing. If I integrate that, I'm going to get something positive. There's my contradiction. 0 is greater than 0. Okay, cool. So we have proved the fundamental lemma. If we integrate against a variation and we get 0 no matter which variation we choose, then our function is identically 0. Okay, here's a corollary. You may have noticed that we didn't have an eta in our previous thing. We actually had an eta prime. So let's see how that changes what we have. If I have a big M that's continuous, and I'm integrating big M against an eta prime for any variation eta, well then m of x is, big M is going to be a constant function. Okay, I bet you can guess how this is going to go. Here's how it's going to go. We're going to integrate by parts. I got to choose a u that I can take the derivative of, and I got to choose a dv that I know how to integrate. Probably what I'm going to choose for dv is eta prime dx, so that v is eta of x. That leaves my u to be big M. My du would then be big M prime, which I'm just going to write as little m for reasons. Okay, and then if I throw this into my integration by parts formula, here's what I get. Here's my u, here's my v, and then the integral of v du. Eta is 0 at the endpoints, and so this piece dies, which is nice. And so I just end up with negative this integral. But look at this. This integral is the integral that we just were in the situation of with the fundamental lemma. We can conclude, therefore, that little m is 0, and little m was the derivative of big M, and so big M has to be constant. Okay, neat. What are we going to do with that? Well, here's what we have. We have some thing that is multiplied by the derivative of some variation, and we're integrating that, and we're getting 0. That was the consequence of saying that j prime of 0 ought to be 0. And so that means by the fundamental lemma, the corollary of the fundamental lemma, I should say, this thing that's integrating against eta prime ought to be some constant. All right, well, let's do a little bit of algebra. Here is what happens, and what we end up with is that y prime is some constant. Like c squared over 1 minus c squared, but I don't really care because c was arbitrary. Let's just rename that some new constant k. If y prime is a constant k, well then y is for sure a straight line. Hooray, we have proved what we thought was true. So here is what we have proved. We have proved that the shortest path between 2 points is a straight line. That's not actually what we proved. Here is what we really proved. If there is a shortest path between 2 points, it has to be a straight line. I am not going to get into the subtleties here of this sort of necessary versus sufficient distinction, because there's a lot more complicated math that you have to do if you're going to deal with that. I think we're going to content ourselves with knowing something about the solution if it exists for the purposes of this 45-minute talk. All right, so let's sort of summarize the strategy that we engaged in here. We wrote down a functional in some way. We constructed a wiggle by adding a certain amount of variation. We fed that wiggle into the functional, and here's what we got. And that was truly some function of a single variable, and so we can do single variable calculus with it. We can take the derivative with respect to a. We're going to assume that we have a minimizer on our hands, come up with j prime of 0 equals 0, calculate, and then concluded something interesting about y. In our case, that y prime was a constant. Let's see if we can apply this strategy now that we've thought our way through this whole wiggle and variation thing. and gotten to the fundamental lemma, I bet that we can apply this strategy more broadly pretty quick. So let's think about how we could do that. Let's say that we just have some generic functional with some generic integrand here. If we do our whole, apply to a wiggle and take the derivative thing, here is what we're going to get if we write down that j prime of 0 equals 0. Well, the derivative of j is the integral of the partial derivative, right? Differentiating under the integral sign. What is that partial derivative going to look like? It's going to be weird. So f really depends on x, and it depends on w, and it depends on w prime. And x doesn't depend on a, but both w and w prime depend on a. And so then if we use the chain rule, we can write down an expression for partial f partial a, which is this business. All right. And then, well, okay. So since w was y plus a times eta, that means that the partial of w with respect to a is going to be eta. And similarly, the partial of w prime is going to be eta prime. So we can throw those into this here, and here's what we get. And then we were really interested when a equals 0. And when a equals 0, w is just y, right? If we collapse out the amount of variation, we get our original curve back. That was sort of the point. Sure. So then as far as we ever cared, partial f partial a is going to be partial f partial y times eta, partial f partial y prime times eta prime. Okay, we're going to do some more integration by parts. Here we go. We are, oh, I forgot a dx here. Pretend that's there. We were integrating the partial of f with respect to a. We can substitute in this thing that we figured out by the chain rule. I'm going to do an integration by parts here because anytime I see something multiplied by a derivative and I'm integrating it, I like to use integration by parts to get rid of that derivative. That often results in something nice happening. I think, again, the clear choice for dv is our eta prime, which means that v is going to be eta. And then that leaves partial f partial y prime to be our u. We are going to take the derivative of that with respect to x, which is weird. But that is what we got to do here because we are integrating with respect to x. All right, so then the second term, let's integrate by parts and put all the pieces together. Here is our uv. Again, since we're evaluating from x1 to x2, and eta is a variation, this will die. It'll go to 0. And then we've got the integral of v du. Okay, so I'm going to take this blue thing and put it back in our whole big integral. And here is what I get. Notice that I can factor out an eta now. And that leaves me behind this red part. So I've got this red part, and it was multiplied by eta. Oh, but this was integrating to 0, which means that once more we have landed in the situation of the fundamental lemma that we proved. Cool. This means that this quantity has to be identically 0. This is called the Euler-Lagrange equation. This is what we can conclude that's interesting about why it has to satisfy this, this partial differential equation. I'm going to write it in two ways. Either that quantity that was multiplied by eta has to be 0, or, if you just add this over, you can see the partial of f with respect to y has got to equal the x derivative of the partial of f with respect to y prime. Hold that thought, because we're going to see it again on the next slide. Okay. I want to think of a special case of this because, in general, this partial differential equation is kind of hard to solve. And it's a little more powerful than we really need. So here's a special case. Look, I've got the derivative with respect to x of some other thing, and that feels weird to me. I think it might be useful for us to go back to our original integrand and think of its total derivative with respect to x. And so here again is this tree diagram. Looks very similar to the one we drew before, but this time we're looking at the dependencies on x instead of on a. So f depends directly on x. And it also depends indirectly on x through its dependence on y and on y prime. And so if we hit this diagram with the chain rule, we get the following. So the total derivative of f with respect to x is the partial of f with respect to y times the the derivative of y with respect to x. That's not partial because y doesn't depend on anything else. Okay, and then we got the partial of f with respect to y prime, and then the derivative of y prime with respect to x. And then we got the partial of f with respect to x that reflects f's direct dependence on x maybe. Okay, so the thing that we just learned from the Euler-Lagrange equation was that the partial of f with respect to y is actually just the x derivative of the partial of f with respect to y prime. So we can replace this here with that. Dy dx is y prime. Dy prime dx I'm going to call the derivative of y prime. Look what I got here now. I've got the derivative of a thing times something else, and then I got the thing times the derivative of the something else, which sounds to me a heck of a lot like the product rule, except I'm going to apply it backwards. And so here is what I get. That is just the x derivative, right, of this thing times this thing. So that's cool. And then I just have this partial of f with respect to x trailing out here. All right, so then if I just subtract this term over, I end up with this equation, which I think you can see is true. So I said earlier that a lot of functionals that we care about are not going to depend explicitly on x because things are autonomous and don't shift, don't change when you shift from left to right. Right, so as long as the integrand of the functional doesn't depend on x explicitly, I bet that we're going to get a nice special case because this partial of f with respect to x is 0. So here's what we've got, and we can think about just adding this back over now, and then integrating both sides, or factoring out the derivative, quote unquote, and getting this, and then integrating both sides. And so we could conclude that f minus the partial of f with respect to y prime times y prime should equal some constant, and this is called the Beltrami identity. So this is a special case of the Euler-Lagrange equation in the case where the integrand doesn't depend explicitly on x. Okay, fun. I feel like we now have some tools that we can confidently apply to various situations that we may find ourselves in. Let us return to the catenary. Sorry, that was a bad joke. We need to more precisely formulate the problem, right? Originally we said like what shape, what function describes this curve that the chain takes. I think we're going to have to turn on our physics brain a little bit in order to formulate the problem more precisely. The operative thing here is that things generally in nature want to minimize their energy. And the particular kind of energy that we're interested in here is gravitational potential energy. If the chain is suspended from 2 points, it wants to hang in a way that minimizes the gravitational potential energy. There's also the length of the chain that we have to think about, right? If I have a longer chain, it's going to go like woo, as opposed to a shorter chain that's going to go like whoop. So here is a more precise formulation of the catenary problem. What function passing through 2 specified points, x1, y1, and x2, y2, with a specified length minimizes the energy, the gravitational potential energy? Okay, I'm going to need a functional, and again, we're probably going to have to activate our physics brain for this. That's pretty common. Like I said, energy in this case is probably gravitational potential energy. We are going to slice, approximate, integrate again. We're going to think of a little chunk of the chain as a point mass, and then the gravitational potential energy of a point mass is the mass of that thing times acceleration due to gravity times the height that it has above the ground. Okay. Well, the mass of that little thing is going to be like the mass density of the chain times ds. Oh, look, there's that ds that I told you was going to show up again, multiplied by g multiplied by the height. I am going to assume here that the mass density of the chain is constant, which is a pretty decent assumption, because otherwise things would get real bad. Okay, so I'm just going to rearrange some stuff here, pull my 2 constants out. And then I'm thinking of the height as y, right? Y of x, the function. And then ds was this that I told you to remember. Okay, neat. So then I just need to integrate that, and I get the total GPE of the whole chain. And in particular, since we're minimizing, we're just going to like take the derivative of this thing and set it equal to 0. These constants are just going to hang out, and then we can divide them over to the 0 side, so we don't even need those. So here's our functional. Where now our integrand is y times the square root of 1 plus y prime squared. Okay. Well, that's neat. We can probably just I'm noticing that there's no x's in there, right? This is an autonomous situation. If I shift the chain from left to right, probably nothing is going to change because gravity is the same if you move 1 foot to the right. That means that we can use the Beltrami identity. All right, so we're going to need to do some calculations. We're going to need to figure out y prime, and no, I'm sorry. We're going to need to figure out the partial of f with respect to y prime. And then we're just going to multiply that by literally this symbol y prime. Here's our function. Here is its partial with respect to y prime. Notice as far as y prime cares, y is a constant. I'm doing this very formally. Yes, there is a relationship there, but just symbolically speaking, y prime considered as a different symbol than y is what we're taking the derivative with respect to. Do a little algebra, clean that up. Looks like this. So then if I throw these pieces into the Beltrami identity, here is what I get. Here is my f. Here is my partial f partial y prime. Now that I've multiplied it by y prime, this y prime ends up being squared. Okay, and then the difference of those is supposed to be a constant. Neat. I'm going to clear that denominator because the square roots are freaking me out. I can now distribute this y through, and then some stuff is going to add to 0, and so here's what I get. That's pretty decent. This doesn't look like too bad of a differential equation to solve, which is kind of surprising. Like, this seemed like a way harder problem than would just be amenable to attacking it with a simple differential equation. This is even a separable differential equation. Here's the algebra for that. I'm not going to talk through it because that's boring. You can integrate this. It's not nice, and I encourage you to try. There is a particular substitution that will make it nice, but I'm not going to say what it is for just a second. I wonder if there's another way that we could approach this problem, though. I like to say that differential equations is the study of dirty tricks. There's a very similar situation, click on that link if you want to read the details, where the correct trick is a trigonometric substitution. And then we're going to work toward a parametric solution instead of an explicit solution. You can see if my y prime was, let's see, I guess a tangent of theta, then I got 1 plus tangent squared, and that should be secant squared, and then maybe some good stuff happens. So let's try that substitution here. I spun my wheels with this for a little while. I think you end up getting something that works. If you make this substitution and dink around with it, you end up with this, which is a first order non-homogeneous differential equation, which is fairly straightforward to solve. This works. I think it feels like the wrong trick. I think there's maybe a cooler, funner trick that we can do. And let's see what that trick is. The trick is sinh and cosh. These are called the hyperbolic sine and hyperbolic cosine. Here are their definitions. They are related to our usual circular sine and cosine in a particular way. If you think hard about the real and imaginary parts of e to the ix, I think you can see what is going on. I'm not going to say too much about it. Here are the things that you care about from these definitions, and you can check that these are true. If you take the derivative of sinh, you get cosh. And if you take the derivative of cosh, you get sinh, which is like one step nicer than the relationship between sine and cosine's derivatives. And there's also sort of a Pythagorean-ish identity going on here as well, which is this. The square of cosh is equal to 1 plus the square of sinh. So this is close to the Pythagorean identity for sine and cosine, but sort of things are in different places. And in particular, I'm liking that I have a 1 plus something squared because that was what my differential equation looked like. Okay, so here we go. I've got my 1 plus something squared. If I threw in like a cosh here, I probably win. No, I'm sorry. If I throw in a sinh here, I probably win. But there's also this c, and then let's see. If this was a sinh, then I think my y would have to be a cosh. I'm going to guess that y is the cosh of x over c. Let's see if that works. Y prime is going to be 1 over c times the sinh of x over c, which I'm hoping will sort of cancel out that c squared that we have up here. Let's see if that works. 1 plus y prime squared is this business, which I don't think is going to add up correctly. Let's see, if I multiply through by that c squared, yeah, I've got a c squared plus this, which is not quite what I want. I would really like that to be a 1, essentially, or this to be the same as some coefficient on my sinh squared. So I think that's probably the wrong guess. What if I modify my guess slightly? If I had a c here, then this would die, and so then when I multiply by the c squared, I think I would get a c squared plus c squared. So here's my revised guess, and let's see if that works. Yeah, okay, y prime now is 1 instead of 1 over c times the sinh of x over c. And if I add 1 to that, and then multiply by c squared, then I can do that Pythagorean thing, and I get that is indeed y squared. So hooray. I have managed to guess the solution to this differential equation by looking carefully at the structure and then knowing about the hyperbolic sine and hyperbolic cosine. Okay, this is cool. So I think that we have a solution, y equals c times the cosh of x over c. I don't think this is the general solution. I feel like we need another constant. I have a constant, but there were several parameters, right? There were several free choices that we had when we were setting up the problem. Specifically the 2 endpoints. I could move any one of the endpoints around however I wanted. And so I feel like my general heuristic is that each free choice that I have ought to correspond in some way or help determine one parameter. So since I have these 2 free choices, I should probably have 2 parameters. Okay. Another thing that I'm noticing here is that c that we had just came from like the Beltrami identity. It was a constant of integration for something a long time ago. It wasn't a constant of integration for the separable differential equation, right? So I think that I probably need like a constant of integration to appear somewhere. So here's another dirty trick. Notice that our differential equation was autonomous, right? It was invariant. It doesn't depend on x, and so it's invariant under horizontal shifts. And so probably if I just replace x by like x minus h to allow for horizontal shifts, that's probably all I need. And so I'm actually going to guess this, and I'm going to let you pause and think for a second about how the calculation on the previous slide would change if there was an x minus h here. The answer is it kind of doesn't. And so you can check that this will also satisfy this differential equation. This is another fun dirty trick. If your differential equation is autonomous and you don't know where your constant of integration is going to go, see if just shifting the independent variable works. All right. There was, however, one more free choice that we had, which was the length of the chain. And so we have landed, therefore, since we haven't considered that so far, right? If we consider the length of the chain, then we land in the situation of constrained optimization. For those of you who have taken a multivariable calculus class, you're having flashbacks to Lagrange multipliers. Yay! It's a little bit surprising that they appear again here. Here's how the Lagrange multiplier situation looks in multivariable calculus. You've got the gradient of f is supposed to be parallel to the gradient of g, right? So del f equals lambda del g. Subtract that over. This generalizes. Okay, I'm going to tell you right now that for the next 5 minutes or so, I want to give you a flavor of how this is going to work, and I am going to be extremely imprecise and wave my hands a lot. Here's the first thing that I'm going to wave my hands about. I'm going to tell you that this generalizes, and you should just sort of think about this sign as meaning whatever derivative it is that makes sense here. You can see I'm being extremely imprecise with this. So our constraint is arc length, and we know how to calculate the arc length. We did that a minute ago. We had some functional for that. We were integrating ds. And so we're saying that that equals some constant, which let's call it L. Okay, so that's our G in the Lagrange multiplier situation. So if we set up, right, whatever kind of derivative makes sense, the function that we care about optimizing, lambda for a Lagrange multiplier, whatever kind of derivative makes sense, the function providing our constraint. Here's what this looks like. The derivative that we care about is the derivative with respect to a of, feeding a wiggle into the functional. I maybe should have written this with w's, but that was confusing when I tried to write it down, so I didn't. So here's our derivative thing that we're trying to optimize. So this is our GPE functional. Lambda the Lagrange multiplier, derivative that makes sense in context, arc length functional. Okay, and then this is all supposed to equal 0. I'm going to use here the linearity of the derivative and the linearity of the definite integral to sort of smoosh some stuff together. I think you will probably believe this is true. And so this is cool. We have actually just landed in the original situation, but with a just slightly more complicated functional. That is a functional with a just slightly more complicated integrand. So that means, like, we can just apply Beltrami to our new integrand. It still doesn't depend on x. Here's what this is going to look like. We basically already done it. That lambda that's here, nothing. It isn't going to contribute in any way to any of the derivatives that we are doing, right? It's essentially just a vertical shift of the y here, and that doesn't really change much. And you can, work through, but you'll find that the differential equation that you get is this, which is basically the same as the previous differential equation, y squared equals blah, blah, blah. Okay. And you can spot that this y minus lambda is just substituting for y. And so the solution to the differential equation will essentially be the same. Just y minus lambda equals c cosine cosh, blah, blah, blah. Add that lambda over, and here's what you get. And you can check that this works, I promise. This is kind of remarkable that figuring out how the length of the chain impacts things just gave us one more parameter that was just a vertical shift. It's kind of remarkable. Okay, now we have landed on something that has the correct number of parameters, 3, lambda, c, and h. That should be a capital C, pretend it is. And that corresponds quite nicely with the 3 free choices that we have of the 2 fixed endpoints plus the length. In the small amount of time that we have left, I will just say that the values probably are going to have to be solved numerically. That cosh function is kind of a pain to work with. But I made this Desmos worksheet, and I'm just going to show it to you. I'm not going to spend much time on it. Just with some sliders that help you see what the effects of each of these parameters are. And I think if you play with these sliders, you can convince yourself that you can hit any 2 points that you want with any length that you want by sort of fudging with the parameters. Okay. I hope that you had fun today. That's all I got. Here's a slide of some further resources that I have. I hope to add more stuff to this slide on the live version on Overleaf. So check back occasionally and see if there's anything new on there. I hope you had a good time. I think I did. And I hope that you are a little less intimidated by the calculus of variations now. Now that you know it's literally just integrals and derivatives of functionals, and you can see how they mostly work in the same way as single variable functions. I have, like I said previously, glossed over a lot of details. I think this would be an interesting place for you to continue your studies. Figure out what those details are. See if you can find like sufficiency proofs and not just like necessity proofs. Work through the details of some of the things that I've skipped over. I think you'll have a good time. Please feel free to contact me if you have any questions about any of the stuff that I have talked about. And I hope you enjoyed.